Let's dive into the core concept: distributed transactions, mutual exclusion, and deadlocks. Starting with this slide, we look at how distributed deadlocks are detected. In distributed system, we present the system state using wait for graph or WFG. The node represents process and a direct edge from the P1 to P2, means P1 is blocked and waiting for P2 to release a resource. To release a resource. If directed cycle or not forms in the WFG, we have a deadlock. The main challenge here is simply maintaining this graph and spotting those cycles across different nodes. So this now this slide detects the detection algorithm generally falls into two categories: centralized and distributed. Distributed approach includes path pushing, edge chasing, diffusion computation, and global state detection. Keep in mind, you just need to understand the high level ideas behind these rather than every specific details. Now, we transition into agreement protocols. Distributed sites often mean need to reach a consensus. For example, deciding whether to commit or abort a transaction in a distributed database. To agree, sites must share information both in normal failure-free scenarios and in environments prone to faults. So here we move to the nine our established system model. We assume n total sites where at most m can be faulty. They communicate reliably with message passing, knowing who sent what. In synchronous computation, in synchronous computation, processes runs in lockstep, receiving messages from the previous step, computing and sending new messages. When handling processor failures, we consider we consider crash fault, omission fault, and malicious faults alongside authenticated versus non-authenticated messages. Now we look into the mutual exclusion algorithm starting. In centralized algorithm, a single coordinator grants permission to enter a critical region. If processes 1 request access, the coordinator approves it. If process 2 asks next, the coordinator holds off until the process 1 finishes and release it. Here, in the trade-off, we are going to see about the trade-offs. So it is fair and easy to implement, but it creates a single point of failure and a performance bottleneck. By contrast, the distributed algorithm using a timestamp, uh, distributed computing using this timestamp, when processes want critical regions access simultaneously, the lowest timestamp wins. One finish, it signals OK, so the next process can enter. So this eliminates the single point of failure, but it requires sending at least two n minus one messages, making waiting for every single process an overhead kill. So finally, the token ring algorithm. Here, an unordered network is arranged into a logical software ring where a total token passes around. As seen in this slide, there is no single coordinator, and if a process crashes, the token simply bypass it to the neighbor. However, losing the token requires complex regeneration, and detecting a crash token versus slow process can be tricky. So that's all. Thank you.